You'd be amazed when you speak with oven manufacturers and solder companies that they get calls for technical support, and they ask the customer for the profile, and the customer doesn't have a profile. So the unknown is probably the biggest screw up, if you want to use that terminology, because you can't possibly be sure that you have a defect-free board. Maybe not now, but also in the future, without actually knowing what your profile is. And if you are having problems like solder balling or voiding or whatever, and you're asking for assistance without that profile, it's impossible for anyone to give you help. So to me, not profiling is the biggest problem.
That's my guest, MB Allen, next on Reliability Matters.
Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Conrad.
Welcome to another episode of Reliability Matters. Most of our episodes feature guests representing specific segments of the electronic assembly industry. Today's episode is no exception. My guest today is MB Allen from KIC. KIC provides thermal profiling hardware and profiler software tools that help define, measure, monitor, and improve thermal processes for electronic manufacturing services. Today, more than ever, thermal management is vital to ensuring a proper reflow or soldering process. There's a direct link between proper reflow profiles and reliability, which makes this topic relevant for any conversation about reliability. MB Allen is the Manager of Applications and Sales for the Americas and Europe. Formerly a product manager, MB coordinated the advancement of new products and features to accommodate customer needs. Her technical expertise, relationships with valued partners and customers, and many years of experience aid in the future development and improvements of her company's product offerings. MB has worked in the electronic assembly industry for 31 years and has been associated with KIC for 30 years, with both national and international positions. MB Allen, welcome to Reliability Matters. Thanks for being part of this podcast episode.
Thank you, Mike. It's a pleasure to be here.
So we've known each other for probably too many years, not too many to know each other, but too many to admit to. We've both been in this industry for a very long time. And I know we've spoken together at workshops and seen each other at shows and symposiums and conferences. But I really only know you from KIC, your employer. Tell me who MB Allen was before KIC. What's your background and what led you to work with KIC?
Sure. So I started out as a banker in New York City, which is where I'm from. I'm from Brooklyn. And
you don't sound like you're from Brooklyn. You totally don't sound like you're from Brooklyn.
After a glass of wine, you'll be able to hear that.
Or if you're angry, maybe, right?
That's true. Very true.
Okay. Well, I hope I never hear the latter.
We moved out here in 1986, and I didn't come out here with Citibank. And 2 years later, I joined the industry as a sales representative. And how I got involved with KIC was one of the lines that I represented. In fact, at the time, I was one of the presidents, early on presidents of the SMTA chapter, which was a very large chapter at the time and a wonderful opportunity for people to learn, especially at that time in this industry. And I had KIC as a speaker several times, and they were still working out of the garage of our owners, and they asked me to be their representative. So I was KIC's first rep, and I did that for several years, and then I joined them directly. It will be 20 years in July.
Wow. I have an affinity for businesses that started out of garages. My business started out of a garage. And I think that sets the tone forever for that business. I think most businesses don't forget their beginnings in a garage. I think it really molds the way a business will grow and how they treat their customers and their employees.
I couldn't agree with you more. This is still a privately held company, family owned. And from the very beginning, the way that the employees were treated was just like a family, and nothing has changed in all of these years. And it's been an honor to work for this family.
That's amazing. So tell me what KIC does. For those who, probably one or two people listening to this podcast that don't know, we do have a lot of listeners outside of the electronic assembly industry. So for their benefit, tell me what KIC does, its products, its services, its mission, etc.
Sure. We work primarily in thermal management. Now, that can mean a lot of things to a lot of people. We started in the industry, in the high temp industry, during the days when thick film substrates were made here in the U.S. Now that's primarily gone offshore. And we created our first automatic system or monitoring system at that time. And that led us later in time to the SMT industry for solder reflow. And so we do monitoring systems whereby we are able to monitor the thermal process during an SMT board assembly in the reflow oven or in curing oven. And we also do wave and other applications that really do have any type of thermal involvement. And that's how we started. And we continue to be on that path. Believe it or not, we had our automatic systems before we even had profilers, which is a definite part of our ecosystem. And we have multiple tools that can assist our customers to make sure that their process is in spec and then is also maintained in spec in accordance with either the solder paste or the PCB itself or the wave solder fluxes, and especially right now, the components. And then we expanded that into what is now Industry 4.0 or Smart Factory, whereby our software, which is our key element, our optimization tools, and our connectivity tools, where we can be integrated into a smart factory or Industry 4.0 type factory for data acquisition.
Cool. So let's break it down a little bit, particularly for those who are new into this business, the assembly business, for new engineers or for people outside of it. We have a reflow oven, which is basically this long conveyorized tunnel with that produces various temperatures throughout the tunnel. And as solder, as a electrical assembly with with components soldered or sticking on top of the yet reflowed paste, that board goes through the oven and is exposed to various temperatures to allow the paste to melt and the solder to melt and to form a bond to solder the board to the component. And various temperatures are required. Yet I'm assuming the temperature has to rise at a certain rate, not too fast, not too slow. It has to cool down probably at a specific cool down rate. It has to be at temperature for a certain amount of time. So your products, from what I'm understanding, do two things. One is they measure not just the temperature in the oven at various zones, but they actually measure the temperature that the oven is allowing the board to rise to. So you have thermocouples that are mounted on a board to make sure that the board and the various components are seeing the temperatures that are required for a quality solder joint. Is that correct?
That's correct. Especially now where the reliability of the solder joints, especially in a lead-free environment, is so important. We have much more challenges now with that. And the whole goal is to give the customer the information that they need to actually set that board up. So it is within what we refer to as the process window for either the solder paste or the components themselves, because they could vary. And it's challenging, especially when you're dealing in a low volume, high mix environment where you need to set up a board. You might have a fast changeover. You need to know that it's going to perform properly in the long run. And part of that process is making sure that the joint, the solder joint itself, is a good, reliable solder joint.
Right. So it seems obvious to me, but just to give you a chance to explain it, this podcast is all about reliability. How does thermal management and profiling directly interact with reliability?
Currently, when a customer has a new printed circuit board that they have to assemble, it's important for them to know how to set up the oven. And the way they set up the oven is by running a profile. So they're going to have some requirements, and that is the solder paste specifications. And they're going to have some requirements for the components and possibly the printed circuit board itself. So the customer has to then decide on what are the settings that are on that reflow oven to make sure that that board is going to be reliable. It's going to meet the specifications for proper solder reflow, and it's going to make sure that it doesn't damage any components. And so the proper profile is very, very important in the reliability of that board and the solder joints in the long run.
Got it. You referenced earlier that this is a challenging time, that there are more challenges, I think you may have said, with regard to thermal management profiling. What are the specific challenges we're seeing today, maybe that we didn't see 10 years ago, with regard to reflow and producing reliable reflowed connections?
That's a great question because it's ever changing. So initially, when we made some changes and we went to lead-free manufacturing, it was quite dramatic. And we were somewhat fortunate in the United States because when it was first making that transition, the European Union had already taken that, and the solder paste manufacturers at the time were developing materials. But over the long run, and when we started actually transitioning in the United States, a lot of those solders became significantly better than the initial stages. So that was a benefit to the manufacturers here in the U.S. That said, there are still challenges when you are reflowing a PCB that's using lead-free materials. And as an example, the temperatures are higher. So the solder reflow temperature is higher as well as the peak temperature. So one of the challenges is the ovens. Do the ovens that the customers have, are they capable of going to those higher temperatures? And so initially we saw some transition to new ovens to be able to be capable of those higher temperatures. And then the second challenge is the components, because the components are the most critical part, obviously. But in order to have a good, reliable solder joint, as I said, those temperatures are higher, and some of the components are quite sensitive. So you have to maintain a balance between the temperatures that are required for lead-free manufacturing and the component temperatures. As an example, if you have a plastic connector on a PCB and that temperature maximum tolerance is lower than that of what the peak temperature needs to be for the solder, once you set up that profile, it's important that you take all of those parts into consideration. Another issue or another challenge is voiding, and I'm sure you've heard a lot about voiding all over the industry.
Yeah,
exactly. You've got parts like LEDs, you have QFNs, and voiding is a challenge for those components. And so that's where, again, the profile comes into play, because it is basically an immediate and less expensive fix to find a profile that will get the board in spec according to the solder paste, but also to minimize the voiding. Other opportunities to do that are longer term and could be quite expensive. And when you're in a low volume, high mix, fast turn environment, often there are not other opportunities to make changes besides the profile.
Yeah, my experience in addition to that is from for those that are not in this business again, flux paste is a combination of flux, which would be a thick liquid, and an alloy, a metal or metals. And when we switched to lead-free, the required reflow temperatures, the melting point of lead-free alloys was significantly higher than the melting point of tin and lead. And that results in, as you mentioned, higher oven temperatures, which result in higher board temperatures. Along that line, because there's a flux component in the solder paste mix, the flux is quite a bit sensitive. It's quite sensitive to high temperatures, because if the flux is exposed to too high a temperature, particularly too soon during the reflow process, it can volatilize and stop working before the soldering process takes place. So although the paste manufacturers accounted for that and allowed the flux components, the activators and all the other components of flux to withstand higher temperatures, my experience is it did push the process much closer to the edge of the envelope, where when we were running eutectic alloys, tin lead, with a lower reflow temperature, the flux wasn't even close to being pushed to the extreme edge of its tolerance. Now that we're with lead-free, I'm seeing some cases, particularly in lead-free, where the solids content of the flux is 2%, if that, that if the oven is just slightly too hot, or the board receives slightly too much temperature for slightly too long, we could have a failure in the soldering mechanism because the flux has lost its oomph, so to speak. It's polymerized and volatilized too quickly during the process. Is that your experience as well?
You've hit the nail on the head. In fact, there are other problems that can happen with that. If, as an example, if your flux has volatilized, just as you just described it, you may not have sufficient flux to make a good solder joint or a reliable solder joint. You could also have outgassing too fast, where you may lose some of the solder paste, or you may have voiding problems. So what you described in that change to lead-free, we refer to as the process window, which means that process window has gotten much smaller. So whereas when you had tin lead, that process window was quite large. So if you had an oven that was fluctuating and you set the zone set points at X, you had a tolerance within that could change, right? You have a board come in the oven, that board is cooler, it's going to bring the temperatures down as the board continues through the oven. Now you're going to heat that up and cool it down, and it has to be done at a certain rate. And so it has to be quite controlled. So the process window, or the variation in the oven, needs to be controlled. And that is where you go from profiling. Next stage would be optimization. And that means, okay, I have this process window. I know what the specifications are. I run a profile, but now I have to make sure it's in spec. So that's where we refer to optimization, where software can assist the customer to find the correct profile within that very tight process window, so that you want to make sure that there isn't a lot of change in the oven. And then the last part, which again you mentioned, that's very important. Now you have product going through the oven and you're producing these boards. You need to make sure that they maintain in spec because of that tight process window. So then again, you have tools that can give you information on a continuous basis for all of your products as they go through and say, okay, this is good, this is good, this is good. I'm starting to see a change, and I'd like to make sure that I'm aware of that before that change is too significant to cause that product to be out of spec. So there are many tools that can help the customers, the manufacturers, to get in spec quickly, and most importantly, to make sure that all the boards are built in spec. There's where your reliability comes in. You can't afford a latent defect, right, once it's in the field, and not be able to identify where that happened. And you have the same problem with, you have the same problem with components, right? If you have a problem with a component and they perceive that it's heat related, it's very important to be able to identify whether it is or not.
Right. And we're going to talk about keeping an oven in spec in just a little bit. And we're also going to touch on the software subject that you brought up. I want to continue down the road of challenges. And we talked about the higher temperatures that reflow ovens have to run at in order to be compatible with lead-free alloys. What is miniaturization done? Our boards are much smaller than they used to be, and they contain many multiples of components compared to quote unquote the old days. Components are smaller, they're denser, they're closer to the board. Many have bottom terminated solder pads on them. Many have large thermal dissipation ground planes, etc. How has that affected the thermal management business, and does that in itself, the miniaturization, the higher density, the lower component heights, the bottom terminated components that we see today, how has that affected the thermal management business?
Everything you describe, just put that all together and imagine how difficult it is for someone that has a brand new board with that type of complexity to find a good recipe on the oven to make sure that that board is processed in spec or processed according to the guidelines of the solder paste and the components. It's very difficult. It's especially difficult because I believe that what we used to talk about a lot, you might remember this, Mike, design for manufacturability.
Sure.
Somewhere that changed somewhere along the line.
I think that's a myth.
I'm sorry?
I think that's a myth.
Design for manufacturability?
Yeah, I've heard it. I've heard people talk about it, but I don't know if there is objective evidence to support the theory that things are designed to be made.
I agree. I couldn't agree with you more. I see some products that customers are trying to build, and I can't imagine the person that did that design without contemplating how difficult it was to be able to, in this case, get a good solder joint. When you have ground planes and heat sinks and top and bottom components of all different sizes and variations. I've seen, back-to-back BGAs on a board with something in between them. And then you've got the combination of the parts that I think I probably used to be able to see when I was younger, but now they're just on there and I just think they're dots. And
right.
As well as some of these, larger components all on the same board. And so, yes, the answer to your question is it has become extremely difficult, and lead-free has added to that difficulty with the miniaturization. It is definitely a challenge for a customer to find a good balance.
All the more need to have a good thermal management system to tell you what you can't see and what you otherwise can't measure.
Correct. You need that data. You need good information. And along with that, you need some help because there are so many variables. If you imagine changing one zone by 1 degree and another zone by 1 degree, or the conveyor speed, all of those variables, it's really an endless amount of changes that are possible. So you mentioned software. That's where that comes in to really help the people with those challenges to try to find an appropriate, not only starting point, but the most optimum profile for those types of boards. It's not easy, I can assure you, and that's where software becomes a key.
Interesting. My friend Mike Butow, who's the editor-in-chief of Circuits Assembly magazine, and he also runs a podcast called PCB Chat, where this podcast, Reliability Matters, is syndicated. He has an occasional podcast episode called The Screw Ups, which I hope I'm never featured on that because here's the title and here's the person's, picture above it. But it's not about the person being a screw up. They tell their favorite kind of screw up stories from the field, which I love those stories. So what are the common mistakes? We'll call them mistakes and not screw ups. I'll let Mike keep that name. What are the common mistakes made using profilers? And then I'm going to ask the same questions about the common mistakes people make using reflow ovens.
Okay. I think one of the most common mistakes is even before using the profiler, and that is not using the profiler. You'd be amazed when you speak with oven manufacturers and solder companies that they get calls for technical support and they ask the customer for the profile and the customer doesn't have a profile. So the unknown is probably the biggest screw up, if you want to use that terminology, because you can't possibly be sure that you have a defect-free board. Maybe not now, but also in the future, without actually knowing what your profile is. And if you are having problems like solder balling or voiding or whatever, and you're asking for assistance without that profile, it's impossible for anyone to give you help. So to me, not profiling is the biggest problem. And then second to that is, you mentioned it earlier, you talked about the challenging assemblies right now. So when you do set up your board, please, you must use the components that are on it, which means a populated board versus a bare board, because you can imagine the differential between a bare board, putting thermocouples in various places, and that where you put the thermocouple on a component. That to me is another error that people make quite often, making an assumption that the temperature will be the same once they populate the board. And then a good representation of that product. Throwing a couple of thermocouples in just randomly does not give you a good representation of the board. Therefore, you will not be able to uncover some problems that you may have later.
And how's that remedied?
The first way it's remedied, I'm going out on a limb here, is that people that are giving boards to contract manufacturers to assemble need to give them the proper tools. And very often, especially when you're doing low volume, you have to build 10, 100, 200 PCBs, and that's how many PCBs they're given without components. So I do believe it's the responsibility of the customer to give their manufacturer the right tools. So they should give them an extra board and allow them to be able to populate that in order to set that board up properly. That's the first part. Absolutely. You kind of can't pull it out of the air, right? And then the second part is when a person is going to profile, to just be conscious of those things that I mentioned. Attach your thermocouples well. Make sure you're not attaching them with the wrong materials, such as Kapton, which will expand when it's heated, and then you're not getting a really good connection of your thermocouple to your component. You're getting more air, which is not repeatable. And a good representation of those components. So when you do have those very small parts and you do have critical places where you have top and bottom components and the edges, make sure you put thermocouples in all of those locations, because those are the keys. And as you mentioned, especially QFNs, BGAs, and things like that.
Let's switch that same question to reflow ovens. And what are people doing, if anything, and I'm sure there's no shortage, what are people doing wrong with their reflow ovens with regard to how they operate them, how they do or don't maintain them, that falls on a profiler to catch, to set up a flag that there's something wrong?
I would say two of the main areas where errors can be had or that can affect the reflow of the board is, one is operator error. You know, the operator could load the wrong recipe, meaning that they load a recipe for board A and it's supposed to be board B, and the size and the density of that board is different. So the oven will not necessarily be able to perform so that board's reflowed properly, whether it's a too high recipe or a too low recipe or just inappropriate for that product. So operator error is one area that comes to my mind. And then the second is really maintenance. You know, you have challenges with fluxes, and it's very important that your oven be maintained properly, that you do due diligence in maintaining that oven so that it's performing the same as it did when you got it. You know, originally when that oven was delivered, it was clean and it was all in, you know, good shape, and it's very important to maintain that. And I see some facilities that do a wonderful job of that. And then every now and then you see someone who has probably never done anything to their oven in the last 10 years. Their reliability is going to be somewhat lower.
So because an oven only knows what temperature a zone's at based on a reading from a thermocouple, if an oven's not maintained and there's flux buildup all through the oven, does that affect the oven's ability to accurately determine the temperature within a particular zone?
Not necessarily determine the temperature, and usually the flux buildup is more towards the reflow area, but it's the control thermocouple in the oven is going to do its job. It's reading the temperature very close to the heater panel, and it's giving that enough power to maintain the temperature there. However, if there is some flux, which is the insulator to some degree, what's happening at the product level may be different. It's the same thing with fan speed. It's the same thing with the blowers to make sure that they're maintained properly. Exhaust is another thing, which I have seen change so much in the last year and a half, where people are adding additional equipment to their lines, but they're sharing exhaust. So imagine when you set that recipe up for a product, a year and a half, 2 years ago, you go to run it now, and then the exhaust is different. So the result of that product's reflow process will change, albeit it's still being maintained, and albeit it's probably still set the same. How it's working may be different just because of sharing that exhaust system throughout the factory.
Interesting. Let's talk about the increase in the volume of and the diversity of electronic assemblies. There's an increase caused by Internet of Things, IoT, and certainly by automotive. And in the world of IoT, we're putting circuit boards in products that never had circuit boards in them before. I was working on a presentation for a webinar we're giving next week, and there's photographs of toothbrushes with circuit boards inside, and sports equipment, tennis rackets with accelerometers built into them, and footballs with something built into them, and examples of electronics that have very high that have to survive in very harsh environments, either from a heat and humidity standpoint, or cold, or vibration and shock and things like that, which the latter particularly requires very high quality soldered connections, because not only does a soldered connection allow the electrical current to be transported through the various components, it also allows the component to stay on the board if it's subjected to shock. So and in the world of automotive, we're not running electric automobiles on 120 volts or 12 volts. We're running them in some cases on thousands of volts, which also requires a much more durable, higher reliability product. And also in the world of electronics, when an electric car is delivered to your home and turned on, it stays on for the life of the car. It doesn't turn off like a fossil fuel powered car would. Its systems are alive and operational for as long as 15 years in arguably harsh environments. So all that being said, is that driving business toward reliability increasing technologies like thermal management and profiling? Do you see a link between the volume of business or the interest in your types of products and IoT and automotive?
Yes, very much so, especially automotive. I mean, we can start with that. Automotive, the regulations that they have, obviously with they're now in doing lead-free manufacturing as well, has become much stricter. There's much more audits. There's many more controls in place. They need to have process control throughout the entire manufacturing of any assembly. It really initially was for more safety type products in automotive, but it has since transitioned to other parts of the automotive, other parts of the car. You mentioned some of those things. If you think about lights, right? So your headlights are now controlled, right? Depending on, you could be on a dark road, the lights will change according to the lighting that's outside to give you more light. Or if there's an oncoming car, it will automatically change so that it's not at the same level that it was before. So those are all things that are maybe not safety related, but they are in fact electronics. So there's definitely more controls going in that. And then you went further. I liked your example of athletics, shock. So if you built a printed circuit board and it looks really good, and you've done some testing, possibly not complete testing, but the solder joint is maybe slightly brittle or not 100%, or maybe you do have voiding, that shock could certainly cause the component to fall off the PCB. one of my colleagues is running the Boston Marathon this weekend, and imagine I know him with his electronics. I'm sure he doesn't want to get partially through the race and not have all of the information he needs at his fingertips, right? So yes, absolutely, it has become more important, much more critical, and the controls that people are implementing in their factory now is much greater than I have seen in many, many years. We've offered controls for that since the inception of our company. I think the I 4.0 and Smart Factory were coming into the world where now the world has kind of caught up to our products. So it has changed significantly.
Well, that's a perfect segue. My next question is all about Industry 4.0. It seems that our industry wants all of its various machines to talk to each other. And to be frank, I don't see a huge benefit in having every machine talk to every other machine. But I do see, for example, profilers and thermal management systems being able to communicate with reflow ovens as a good use of machine to machine and machine to business communication. So how do profilers or thermal management systems talk to ovens? How do they interface with them? And what information is sent or exchanged? And how does that benefit the assembler?
There are several aspects to that. The first I'm going to address is your question regarding the ovens themselves. One of the examples I gave you earlier was human error, where an individual could potentially change the oven with the wrong recipe. Systems like ours talk to ovens or communicate with ovens. We can exchange information. And if that information is incorrect or that recipe is incorrect, we are able to identify that when the board begins to enter the oven via barcode, as an example, or through other information that we can get from an MES system or the oven itself. So one of those points you made as far as making sure that things are in control, by communicating with the oven, we can do that. Another part of that is downtime. Another part of that is the information that you are collecting. So if you can eliminate some downtime by sharing information with the oven, we can transition more quickly. And that also comes to optimization. So back to what I was saying about software, if we can optimize a process, share that information or that recipe with the oven, by talking to it, that changeover can happen more easily. And then you move into, you were saying machine to machine, and information. I call it usable data because, as you said, people are collecting so much data, and we live
in a world of big data.
Exactly.
But what's big data if we don't know what we want
exactly.
and what we're trying to extrapolate from?
I have a presentation that I do where I have a picture of the cloud, of a cloud, and the cloud is crying with, just pouring rain and crying because there's only so much I can put up in that cloud, right? And
Right.
I have to be able to use it. I have to be able to get that and make use of it. So in order to get that data, you want it to be usable data, and then you want to be able to use that for the analytics part. And I think that's the most important part about Industry 4.0 or Smart Factory, is the use of the data to analyze my process and make it better. And I believe that some people kind of lose that part of the idea that it's not for someone to just spend a lot of money to have all the data, but it's to make me better. So how can I use that? How can I improve my process? And again, how can I reduce my downtime? How can I improve my product so that I know it's in spec and I can prove that because I have the data to back it up. And most importantly, how can I make my product even better? Obviously, that's going to give me an edge over the competition, but it's also going to make me more profitable. If I'm reducing my waste and reducing downtime, I'm going to become more profitable as well. So there's definitely more to the Smart Factory other than just collecting the data. It's how you use it and why you're using it and the benefits you're going to get out of it to make a better product.
Yeah, the useful takeaways. So there's lots of, I shouldn't say lots, there's more than one profiler on the market. And I'm going to make a blanket assumption, and I have no idea if this is accurate. So slap me down if it's not true. I see two sides to that technology. One is the mechanical side. It's a box that doesn't get burned up. as it goes through an oven, and thermocouples that attach to a board on the profiling side. And then it's the collection of that data and the software that crunches the numbers and provides useful information to the customers. So my question is, it seems to me like it's the software that really differentiates one thermal management product from another thermal management product. How does the software influence the effectiveness of the product and the results achieved? And if someone has a profiler that's several years old, at what point, based on the evolution of the electronic industry with, as we spoke about before, higher temperatures and miniaturization and higher larger ground planes and more thermal disposition or thermal management on a board itself, how old would a product be, yours or anyone's, just in general, where an upgrade would really be worth considering based on software? And if there's a point in time, say, for example, 5 years old, 10 years old, where with newer technology that wasn't around when that product and that product software was designed is now being implemented, at what point does it make sense to either upgrade the device or upgrade the software in the device?
Definitely a two-part question. I couldn't agree with you more about the software. If someone asked me what I do, I would probably say we're a software company before I'd say we're a hardware company, because that is really the foundation of what we do and how this company was founded. It was software. And our prediction model and our optimization model are the key to that. Our focus is on giving the customer the tools to find a good recipe, to get them there quickly, to reduce their downtime, to overcome the obstacles of these very challenging boards by giving them software tools to look at all of the components and then help them to find the proper recipe. So software is a key. When you take it to the next step and you go into what we would say continuously monitoring the process for all the boards, again, that's software related. Those are all, that's the data acquisition that we're getting from our systems and then crunching those numbers and providing the customers with information on each and every board. Traceability, the use for MES systems, troubleshooting, and so forth. So absolutely 100% I agree with you. It's software. Hardware is a little different. Hardware can last forever. I think that the main things that would cause people to change is the hardware matching the software that they want or that they need today. Because of course, as products progress, they are also going to progress with software. So as new pieces of software are available, they may only be available with the more current products. So that might be one reason. Size is another. Changes in printed circuit boards due to miniaturization, that's really important. If you have someone that's doing a smaller PCB and they need something that's not very wide, that may be one time. And the last thing I would say is probably temperature tolerance also. Because as we went into lead-free, some of these temperatures are getting hotter and hotter. I know that one possible solution of avoiding voids on QFNs is a higher peak temperature. And that may not be great for all of your components. So you need the software to make sure you balance that out. And then you also need the hardware to be able to sustain those temperatures. And then other parts to that is, just like a car, you have a car for some years and you want to buy a new car and you want to get the car with what's current, right? What are what's the newest technology that's available? And how is that new technology going to help me? From our perspective, it's giving you, we say smart. So we want to give you smart tools, the tools that take away the time for you to try to figure something out, and give you that information right away. So I would say those are the two, probably the best reasons why someone would make a change or add products for those reasons as well.
Very good. And my last question has to do with IPC standards. For those who are outside of our industry, IPC is one of our industry trade groups, and we have a collaborative approach to creating standards. It's kind of all countries heard from. And we create and publish standards that our industry is subjected to. Are there relevant standards regarding reflow, the quality of a solder connection, that profilers or thermal management systems can assist in the compliance of those standards?
Yes, there are. I was on a committee some years ago that was definitely related to specifically profiling. What are the most, like you just said, the standards for deciding if this is a good solder joint? That was one thing that IPC did some years ago. And then recently now more with the IPC Connected Factory Exchange, this is where we're taking that information and sharing that with MES systems or homegrown systems or whatever type of connectivity you want in the factory. So IPC is definitely on that. I do believe that recently there was also some additional changes to the standard I referenced at the beginning, but I'm afraid I don't have that information in front of me.
Yeah, no worries. You and I both do a lot of travel. Where's your next trip?
My next trip is Monday, and that is to Tennessee. And I don't believe I have another day home until the last week of May.
Nashville, Tennessee, by chance?
Starting in Nashville and then moving over, going east, and then coming back to Nashville, yes.
I love that city. That's a fun city. You can have a lot of fun in that city after hours, even during the day.
I hope to actually get to the city. You know, when you travel, as you know very well, when you travel for business, you often don't get to see too much except for our wonderful customers.
The hotel room, the car rental lot, and the airport terminal, right?
And
a few lobbies
restaurant somewhere.
Yeah. Exactly. Hey, MB, this has been a thrill. Thank you so much for being my guest today.
It has been my pleasure. This is a topic that I love. I love helping customers, and our company is very dedicated to technical support and customer support. So it is definitely my pleasure to be speaking here with you today, and of course working with you. As always, that's a pleasure.
Oh, thank you very much, and the same back at you. I do enjoy having guests on with a lot of passion for what they do, and you're certainly no exception. In fact, you probably come close to setting that bar. So I appreciate the passion you have for your part of our industry. I think it's an important part of our industry. It all definitely ties into reliability, which is what this podcast is all about. So thanks for being my enthusiastic guest today, and I really appreciate your input and your wealth of knowledge, and I look forward to seeing you wherever I'll see you next.
Oh, me too. And it has been my pleasure. Thank you.
Thank you, MB. Well, that's another episode. Thanks for listening to Reliability Matters. If you like what you hear, please be sure to give us a like. Just click the like or heart button below. If there are any reliability-based questions you'd like to have answered or specific topics discussed, let me know. I can be reached at mike@mikeconrad.com. That's Conrad with a K. Don't miss another episode. Subscribe to Reliability Matters on iTunes or follow us on Spotify. You can also listen to us on iTunes, Spotify, aqueoustech.com, PCBchat.com, Spreaker.com, or our newest affiliate, Ascendo Reliability, on reliability.fm, a site dedicated to all things reliability. Once again, thanks for listening. We'll be back soon with another episode of Reliability Matters. In the meantime, keep doing it right.